Hello, and welcome to this presentation on synthetic data generation for MlFinLab and how to use it to augment your models. And just really quick about myself, my name is David. I'm an apprenticeship researcher at Hudson and Thames. I'm doing my master's in computer science in artificial intelligence and machine learning at Portland State University. And my research topics focus on evolution strategies, specifically using differential evolution to optimize option strategies. And a quick overview of what we're going to learn in this presentation. And the first question that we need to answer is, why do we need synthetic data? Even though we live in an age of abundance of data that we can Google mostly anything. If we just go right now and Google Microsoft stock returns from 20 years ago, we can pretty much get it in a few minutes. So why do we need synthetic data? And next, I'm just going to overview the synthetic data generation module that we created in MlFinLab. It includes how to create synthetic correlation matrices using the binds and extended onion method, using the Hierarchical Correlation Block Model, or HCBM, using various bootstrapping methods such as row, pair, and block bootstrapping, and how to use CorrGAN. And for generating time series, we have, again, the HCBM model, and we will show how to create correlated random blocks and how to discriminate their underlying distributions. So why do we need synthetic data? As I mentioned, if you can just Google anything that you want, why do we need synthetic data? And one of the main reasons is that acquiring historical, reliable, and bias-free that are complete, even stock returns, can cost thousands of dollars. Just these data sets are really expensive. And the reason they're expensive is because, like I mentioned, it has to be reliable, bias-free, and the reason that you cannot just get it from Google or Yahoo Finance is that you have no guarantee that the person that created that data correctly adjusted for dividends calculations or stock splits or anything like that. So, getting the guarantee of that it can be really expensive. Another reason is privacy restrictions. Financial data, for example, you have some bank loan information that can contain personal identifiable attributes of customers. And due to new privacy laws such as GDPR, even if you get your hands on some of that data, you're not able to easily share it. You can just put it in a hard drive in your shared machine and share it with anybody. You'll get in a lot of trouble by sharing private information. Another reason is that historical data is inherently biased. Historical events happening only one way. For example, this year we have the COVID crash. So, let's say that you created a model and want to make sure that for the next COVID scenario, it will still perform adequately. Since COVID only happened once, it's really easy to overfit, for that single event. But if you're able to create multiple synthetic scenarios that have the same properties of the COVID crash, it'll be easier to prove that your model was not overfit and it actually works. And there are many more reasons. As I mentioned, it's to reduce overfit. The more data you have, the easier it is to prove that your model is not overfit. And besides GDPR, at least in the US here, we have different privacy laws such as FERPA and HIPAA. Also, to reduce your data set imbalance, if you have your data set and just have too few classes, if you're able to generate a few classes and actually balance your data set, it will make your models more robust. And another reason is to be able to train more complex machine learning models. For example, deep learning, it requires vast amounts of data. So if you're able to generate even more than what you have, it will be easier to train it. And some of the challenges of creating synthetic data is, first one is that it maintains the original statistical and structural properties of the data. It's not enough just to grab NumPy's random normal distribution and generate data, right? That would be pretty much useless because you want, from the data that you want to synthetically create, you want to keep those properties. It also has to be fast to generate. You have to be able to generate an arbitrary number of data points and as many features as you want in the least amount of time possible. It would be pretty much useless if you have some functions that create just a few data points in a few days. It would be really hard to use it. And another, as I mentioned before, privacy is the main reason. Just transforming your data is not enough. And let's say you have some bank loan information, right? You can just apply some box-cox transformation and say like, oh, here's new data, but it's underlying privacy information is still there. So you can just transform the data and call it a day. And the solution that we came up with is the data generation module in the MlFinLab. It specializes in correlation matrices and correlated time series generation. and implements the various methods from several authors that you see included here in the slide. And I will start with how to generate correlation matrices using the binds and extended onion methods. And just a really quick overview of what the correlation matrix is. It is constructed by using the correlation of stock returns over a defined time frame. And Pearson's correlation coefficient is the most commonly used correlation metric. And as you see here, we have a formula. And you have to remember that Pearson's only captures linear relation in your data. So if your data has a relation other than linear, you'll have to use other methods. And actually, our codependence module in MlFinLab gives an overview of all the different methods, codependence methods that you can use. So I recommend checking that out. And correlation matrices they're useful for risk management, asset allocation, instrument selection, pricing models, you name it. They're a really useful data structure in finance. So if you're able to generate it synthetically, it will really help our models. And I'll start with the binds method. The binds is a statistical and graphical tool for modeling dependent structures of high-dimensional probability distributions, and they have been proven to be useful and flexible tools in high-dimensional correlation modeling. And that's just a lot of words for saying we can use binds to model the high-dimensional partial correlations that are useful for generating correlation matrices. And we use a substructure of the binds that is called the partial correlation binds. And there's binds is just a graphical structure, and it can have different underlying structures, such as regular binds, D binds, and C binds. And actually, the one you see on the right is called a regular bind. As you see from the graph, it's just a graph structure. You have your nodes, and you have some edges, and then the edges show that how the nodes relate to each other. And partial correlation binds, they measure the degree of association between two random variables while controlling for a third random variable. And each edge of the bind is identified with a partial correlation coefficient. So each edge has a value between -1 and 1. And on the bottom, you will see the example of a C bind on the left and a D bind on the left. And you'll be able to see why it's called C bind, right? You have on the left, the C bind, you have the nodes and the edges that how they're connected looks kind of like the letter C. And on the right, and the D bind, the edges and the nodes kind of look like the letter D. So that's where the names come from. But it is just different representations for the same amount of information. And how we use the binds method to generate correlation matrix? The only thing that we do is traverse the partial correlation bind, and then we calculate real values from these partial correlation values. And the partial correlation values are sampled from a beta distribution. And here in the bottom, you will see the result of creating a correlation matrices using on the top the D-bind method and the bottom the C-bind method. And on the right, you will see the underlying distribution of the pairwise correlation coefficients. And yeah, you will see that most likely looks a little bit similar to some of the correlation matrices that you have generated from your stock returns. The next method is the extended onion method. It iteratively creates a correlation matrix by starting with a one-dimensional matrix, and then it just grows out or adds a layer to the matrix one dimension at a time to create the dimension required. So you can think of it as starting with the one-dimensional matrix and just adding one layer to the onion one at a time, so you can create your correlation matrix. And the reason that this is possible is the fact that any correlation matrix of a defined size can be partitioned as a correlation matrix of a smaller size. And this is shown in the function we have here in the bottom left. So R is the correlation matrix, and we have the dimension of k+1 on the left. And on the right, we can see that there's an R of a smaller dimension, which is dimension k, on the top right of this matrix. And C is the C factor is the correlation vector of R. And you can see if we combine these two terms in a matrix, we can represent a higher dimensional k+1 correlation matrix with the smaller one, k correlation matrix. And on the right, you will see the result of creating some correlation matrices using this extended onion method. And you will see it's a little bit similar to the binds and to the binds method. Yeah, and you may most likely you recognize it looks a little bit similar to some correlation matrices that you have generated. The next method for generating correlation matrices is the Hierarchical Correlation Block Model, or HCBM. And this model consists of correlation matrices that have a hierarchical block structure, where each block corresponds to correlation cluster, and they are defined as a set of nested partitions, which where each partition is subdivided and partitioned again for the defined number of levels, where the correlation strength increases the higher the depth or the level. And you can see here in the picture on the right, there's a few HCBM matrices. And you'll see there are some squares. Those are the blocks of the correlation of the HCBM matrix. And each block has smaller, I guess, blocks inside of them. As you will see, the smaller the block is, the higher is the correlation strength. And yes, and this is how you create your HCBM matrix. And well, as you can see here, this is an ideal structure. The HCBM, you most likely will never, if you compute the correlation matrix from your stock returns, you almost never see such a perfect, I guess, a structure from your correlation, right? But a way that we make it a little bit more realistic is just by computing one permutation of this correlation HCBM matrix, and we show it here. So here on the right, they're the same correlation coefficients, they're the same matrix as the slide before, but just one permutation over. And you will recognize that's a little bit more realistic and most likely something you have seen before when you generate your correlation matrices. Another method to generating correlation matrices are bootstrapping. We will overview the row, pair, and block bootstrapping methods. So just real quick definition of bootstrap is just a statistical method for sampling from an original data set with replacement to create a new data set. And this new data set will maintain the statistical structure of the original data set, such as the mean, standard deviation, variance, and etc. And you're useful for reducing the overfit of your models, and they're usually using ensemble algorithms such as AdaBoost or random forest. And we can leverage this method to create our correlation matrices. And I will just start with the row bootstrap method, probably the simpler of all of them in my opinion. And the way that this one works is samples rows with replacement from the original data set to generate a new data set. And the implication of sampling with replacement is that the new data set can contain repeated data from the original data set. And here on the bottom, just to illustrate this, I have my original data set on the left of size T by N. You'll see it has 1 through 100 rows and A through Z columns. And to generate the row bootstrap data set here on the right, this one has the same size as the original one, T by N, but it doesn't necessarily have to be of the same size. And you will see how, by using a random number generator, we just sample a random number from 1 to 100 in this case, to get a row from the original data set, and just in sequence insert it in the row bootstrap data set until we have the number of rows that we desire. And just one thing to keep in mind, like I mentioned, the row bootstrap data set doesn't have to be the same size as the original, but you also don't want to make it too small. If, for example, you make the row bootstrap data set just 5 rows, you won't be able to maintain the structural properties of the original one. So you have something to keep in mind when you create your correlation matrices with row bootstrap. The next method is pair bootstrap. This one is a little bit different than a row bootstrap. I'll just show real quick. With the row bootstrap, we graph as an input a correlation matrix and we output a correlation matrix. With the pair bootstrap in MlFinLab, we actually input the raw returns that you have from your stocks. And with that, we generate a correlation matrix. And the way that it works is that it samples pairs of columns with replacement from the original data set to generate the correlation matrix. So here we have the same original data set, T by N. We have 1 through 100 rows and A through Z columns. And on the right, I'll just show how you can, with a random number generator, you can just graph random columns to create pairs, data set of bootstrap pairs. And here on the top right, you see they have 1 through 100 rows and A, C columns. And with this one, since there's our stock returns, I can calculate a single correlation coefficient from each pair. And I will use those pairs to populate the resulting correlation matrix. Here you will see how, well, from the stock returns and the top, I have the original data set's correlation matrix. And the bottom is a paired bootstrap correlation matrix. And you will see how it keeps the same structure as the original one, just the correlation strength or coefficient changes depending because we're sampling, from the original data set to generate that. So, yeah. The next method is the block bootstrap method, and this one is the same idea as the row bootstrap. So we have as an input that correlation matrix, and what we do is just sample blocks of data from that data set with replacement to generate a new data set. And each block can be a size of equal to or less than the original data set. And the way that it works is that you define a block size and you partition your original data set in that defined number of blocks. And for example, the original data set here in the bottom, we have the same t by n dimension, and we have a block size of 2 by 2. So here on the top left will encompass rows 1 through 2 and columns A through B. And then the next one will be rows still 1 through 2, but columns C to D and so on. And our implementation doesn't allow overlapping blocks except on the edges if the data set is not cleanly divided by the block size. But it was the same idea. I use a random number generator to generate the block number that you want to grab from the original data set, and just stitch it sequentially in the new data set until you complete all your data. The next method to generate correlation matrices is CorrGAN, and is how to generate realistic financial correlation matrices. And I will explain what makes a financial correlation matrix realistic and how it differs a little bit from the other methods that we have seen. So first question, how to generate realistic data sets? Given your data set, how to sample from its feature space, right? So here on the right, we have just a picture of a few faces. And given the feature space of human faces, how do you sample from it, right? You don't want to just sample all the colors possible in, I guess in a 10 by 10 picture or something like that. You just want to grab the feature space of human faces. And there have been a few models that people have been able to come up with. One is autoregressive models, variational autoencoders, or generative adversarial neural networks, or GANs. This actually with CorrGAN comes from, because it uses a GAN. And GANs have been able to produce really good results in a wide variety of domains. So these pictures on the right, actually, they come from whichfacesreal.com. And one of these faces is not real. And they really look human and real. So it just speaks how GANs are really powerful at generating realistic data sets. And what makes a financial correlation matrix realistic? So researchers have been able to identify 6 stylized facts that financial correlation matrices have that other correlation matrices don't have, that makes them realistic. And I'll just go through all of them in the following slides. But here on the right, you'll be able to see how the same comparison. Here on the left, we have a correlation matrix calculated from real stock returns. On the right, we have the CorrGAN generated correlation matrix. And well, maybe if I didn't tell you that, you won't be able to know which one is real, like in that faces picture. But this is how it speaks how GANs are really powerful for this. So the first stylized fact is that the distribution of pairwise correlations coefficients is significantly shifted to the positive. And I will show this by here on the left picture, we have CorrGAN is, well, empirical pairwise correlation distribution is the shaded red on the left picture, and CorrGAN's pairwise correlation distribution shaded blue on the left, and they're overlap with each other. So you will see how CorrGAN's and the empirical distributions look about the same. There's some discrepancies on the tails, but they look really similar. But if you compare it on the right with the pairwise correlation distribution with other methods, you will see that other methods are not significantly shifted to positive. They have a mean of almost 0. They have several values that are negative. So that's what makes correlation matrices realistic. It is one of the stylized facts. The next 2 stylized facts are that the eigenvalues follow the Marchenkine-Pastor distribution. That means that there's a very large first eigenvalue that symbolizes the market, and it is followed by other large eigenvalues that symbolize the industries. And here in the bottom left, we have the same comparison. We have CorrGAN and empirical overlap with each other. And on the left, you will be able to see that they're similar. There's the first eigenvalue is really high compared to the other ones. I think slowly you see a few more high ones until it levels out. But the eigenvalues for other methods, they are just all about the same. So there's another tell that CorrGAN is able to generate realistic matrices. The fourth stylized fact is that the eigenvector entries follow the Perron-Frobenius property, which is that the first eigenvector has positive entries. And here in the picture, again, you will see on the left, empirical with CorrGAN overlap with each other. And you will see that all the eigenvectors are positive. But on the right, you will see other methods. Even though most of them are positive, you will see some that are negative, thus violating this property. The fifth stylized fact is that the correlation matrix has a hierarchical structure of correlations. And on the left, on the top left picture, you will see an empirical correlation matrix, and the bottom left, you will see the CorrGAN correlation matrix. And the hierarchical structure is, if you remember from HCBM, are kind of the squares that show up in a correlation matrix. And from this picture is best illustrated with the dimensions 0 through 20. You'll be able to see some squares that form, and that's the hierarchical structure. But if you contrast it on the right with the correlation matrix generated by other methods, you're barely able to distinguish any structure of correlations there. Yeah, it looks, even though it's not random, it looks random, but that's how you're able to tell if it's not a real correlation matrix. And the last stylized fact is that the scale-free property of the corresponding minimum spanning tree follows the scale-free property. So that means that the degree count of the minimum spanning tree generated from the correlation matrix decays following a power law. And as you will see here on the bottom left, is that we have CorrGAN and empirical overlap with each other. You'll see how it starts really high at the degree count, but it just quickly decays as the number of nodes increase. But on the right, you will see that the degree count decreases almost linearly, if you can see. So definitely they don't follow a power law. And yeah, and this stylized facts are what makes financial correlations realistic. CorrGAN is not able to perfectly capture all of these properties. The author especially notes that the pairwise correlation distribution, the tails difference, is significant, but this is still an evolving theory, and most likely will keep getting better. And we're going to switch how to generate the synthetic time series. I'm going to start with the Hierarchical Correlation Block Model, or HCBM, that we saw from the previous slides. And just to recap HCBM really quick, HCBM is defined as a hierarchical block structure where each block is a nested set of partitions, where the higher the level or the depth, the higher the correlation strength. And by using the HCBM, we can actually generate the time series by using a multivariate time series and input this HCBM correlation matrix. And the underlying distribution can be either Gaussian or the student's T distribution. And Gaussian, you will recognize that is the distribution for a normal random walk, that even though it's similar to stock returns, it's not able to capture heavy tail behavior correctly. So that's why we also offer the student C distribution that fits much better to real returns. And here on the picture, you will see the HCBM matrix on the left. On the right, you will see the time series that were generated by using the HCBM matrix on the left. So all this time series, if you compute the correlation matrix, it will look, well, it will have the same correlation coefficients as the HCBM. But as we talked before, even if you compute the correlation matrix from these distributions, it won't exactly look like the HCBM because that's an idealized structure. But if you do enough permutations, or if you do some clever computations, you're able to recover this HCBM matrix structure. And the last method that we have for generating time series is how to generate correlated random walks, and how to use GMPR to discriminate the underlying distributions from them. And well, in order to generate correlated time series, the way the authors define this is that you have multiple time series, and each one has the length T. So you have, let's say, for example, here would be 200 time series, and each one of this has a length T. And that length T of the time series can be subdivided into K correlation clusters. So you have your length T divided into K correlation clusters. And each of those K correlation clusters can be subdivided into D distribution clusters. So you have multiple structures embedded into each time series. And each correlation and distribution cluster can be generated with a normal, Laplace, or student's T distribution in MlFinLab. And the way we we're able to discriminate the underlying distributions of them, right? Because you're generated with all these distributions that I showed here, normal, Laplace, or student's T. But once you have the distribution, how do you discriminate those distributions, right? Once you have a time series. So we use GMPR for this. That is, I'm not going to go into too much detail. I'll just show a few pictures in the following slides. But if you want to learn more about GMPR, you can just visit our codependence module in MlFinLab, which gives a nice overview of it. So here on the bottom, there's a few parameters for generated correlated time series that the authors of the paper gave us an example. And just shows how to generate the time series that only have distribution information, which only is the D distribution clusters. or only has dependence clustering, which is the K correlation clusters, and how to generate them when we have a mix of both with different strengths. So to generate that time series that only has distribution clusters, and this example is only 4 distribution clusters, we show here, we don't show exactly how to generate it here, it will be in our module, but here we have the resulting time series on the bottom left of using the values from this table over here. We can generate this time series on the left, and using GMPR, we can plot that dependence matrix and discriminate those 4 underlying distributions that are in the time series on the left. The next time series is the dependence clustering. It only contains dependence clusters. And in this case, there are 10 dependence clusters from the table that we show in the previous slide. And this is a resultant time series. And when you create a dependence matrix using GMPR, you're able to separate all these 10 clusters and visualize them. And the last one is how to create a mix of distribution and dependence clusters. And here we show the time series on the bottom left. On the right, the dependence matrix using GMPR. And in this case, this time series has 5 distribution clusters and 2 dependence clusters that GMPR is able to separate. And just to conclude this presentation, we have seen synthetic data generation is a challenging field with many requirements. We have seen that it has to maintain the structure of the original data. There's several privacy considerations. There's the speed of how to create them. It has many requirements. It's a challenging field. And generating data that inherits the properties of the original data is difficult, as we have seen with CorrGAN. Only for correlation matrix, there's 6 stylized facts that we have to take into account for the correlation matrix that we generate to be realistic. So it's difficult to do this. Even with CorrGAN, even with the latest tools, it's still not perfect. It's not perfectly able to generate all these stylized facts. And our current tools still need some work to make them perfect. As I mentioned, even CorrGAN, the latest one, still not perfect. There's some discrepancies on the tails, but they just keep getting better. And MlFinLab aims to close this gap and enable you to augment your model. So hopefully you'll be able to use these tools, generate some correlation matrices, and just keep augmenting your models. Thank you.